All righty, friends. How y'all doing? Good to see you guys. Good to see you guys. So today we're going to keep going a little bit through here, and we're going to take a little bit more about Riemann sums and how this eventually gets us into dealing with a definite integral. Now, we kind of actually looked at sums yesterday, left and right sums, and where that really is not a stretch further. It essentially is the same thing as what we would call a Riemann sum. So here's what Riemann sum basically says. It's a little formula here. And this one came around, Riemann lived, he died back in, I think, 1855 or 56, something like that. So this is a fairly newerish type theorem. And basically, what Riemann basically said was, he said, all right, say that we are adding up a whole bunch of stuff, a whole bunch of partitions or rectangles. He basically said, I believe that a Riemann sum that would approximate the area under a curve would be equal to something like this, C sub I. Now notice, it's essentially the exact same thing we looked at this weekend. The only thing you got to remember here is that C sub I could be anything, any x value between this x minus x time to the I minus 1, C1, or that's C sub I, I'm sorry, and x sub I. Remember this x sub I minus 1, that's the same thing we get when we're dealing with a left sum. That's essentially the x value for a left sum. And we get this value over here, the x sub I. That was essentially the x value we looked at last class for a right sum. And again, we don't have to go too terribly long on a lot of this kind of stuff here. So, one other little thing I want to remember here is what a partition is. Okay, so this delta x, remember what that currently is. That delta x is the same thing as the b minus a over n. So, given a function, we did this again last class, but let's just go and start here a little bit more as we kind of dive into it just a bit here. So given f of x equals 1, right, and I'll finish off that function here in a second. Write a right Riemann sum for the area under the curve from 1 to 4. So let's give ourselves an area under the curve here. Well, first of all, let's finish giving ourselves an equation. I guess I should probably fill that in right there. And we're just gonna make this regular over root x. So the left sum, using this idea, so we can use any c sub I between these two. We're gonna use a right Riemann sum, so we're gonna use x sub I here. So if we remember back, we need to first figure out what our partition length is, b minus a over n. So we got to know what that is. And b is our upper bound, and a is our lower bound. So 4 minus 1 all over n, that would be 3 to the n, 3 over n. So if we're plugging all of our information in here, so from 1 to n, and our width, it's not going to be delta x, we're going to use 3 over n, times f of, now remember what's going to happen here. Actually, let's write this up here just so we remember. Delta x sub I times f of a plus delta xi. Okay. So that was what our right Riemann sum was, or right, we called it a right sum. We didn't actually call it a Riemann sum yet. We can go ahead and call it a Riemann sum at this point in time. And that can be 3, so delta x, that'd be 3n times f of our a value. Well, that's where we're beginning. So f of 1 plus delta x, so 3 over n times I. And again, we dealt with this in class. We did a couple of these on the last video as well. And it's just a way for us to find a way to write how to determine the area under the curve. And in this case, now we can get rid of our function. We can actually use our actual value. So the actual value for f is 1 over the square root of x. So that was our f. And we can plug our 1 plus 3i over n. And we end up with a right Riemann sum that we can use to approximate the area under the curve. Well, what ended up happening here is mathematicians, they ended up going a little bit further. They said, well, we might be able to do something more with this. And they defined something called a definite integral. Now, a definite integral, we've already looked at indefinite integrals. It turns out these definite integrals are also tied to these Riemann sums. They said, all right, let's let the width of these partitions, so the b minus a over n, let's let that approach 0. So essentially, we don't have rectangles. These rectangles essentially turn into a whole infinite number of line segments. So the delta x is approaching 0. That means our n, our number of partitions, is approaching infinity. So our base then is approaching 0. So the height is really all we're adding up. And so the definite integral really is all these Riemann sums added together. It turned out these Riemann sums can be written as what we call a definite integral, where this is called our upper bound. We've already talked about dx. That was called a differential, our upper limit. A is our lower limit. And dx, that's our differential, or what we're taking the integral with respect to. And so instead of trying to write an area expression as a summation, we're just going to write it as a definite integral. So for instance, say I give you a function like this. And we'll let this be y equals the square root of x. And we're going to do this from 1, 2, 2, 3, and 4. If I wanted to know the area under this curve, so in other words, if I wanted to find the area of all this stuff under the curve, down to the x-axis, that would be equal to the definite integral. A is the lower limit, so here's my lower limit, it's at 0. B is my upper limit, so this would be 0 to 4. So instead of writing it as a Riemann sum, we can actually write this as some integral expression. So this area would be equal to this particular part. So as long as this is a non-negative area, we could say that the area under the curve is equal to A to B. So we're starting off with a little bit of theory, not much, just a little bit of theory. When f of x is continuous and non-negative from A to B. Well, this continuous thing, that's kind of an interesting idea right there. F of x is continuous. Because we had a theorem before, and the theorem essentially is just a little statement. It just said differentiability implies continuity. So if I told you that a function was differentiable, you'd come back and say, oh, if it's differentiable, that means it is continuous. Well, when we take the derivative of a function, it goes down a level. If we integrate a function, it goes up a level. So essentially, the function is the derivative of the integral. So we can actually take this statement and we can come up with a second theorem to this that's actually related to it. Continuity implies, the word is integrability. Now, where the differentiability implies continuity, that comes up a lot on the AP test. The continuity implies integrability, not so much. So don't worry too terribly much about it. But here's what it essentially means. If I have a function, if it's continuous, that means I can find the area underneath the curve. Continuity implies integrability. Now, likewise, it doesn't mean that if I can take the integral, that it's automatically continuous. So, for instance, take a function like this. Make that an open dot there. Make this a closed dot here. Okay. I can still, under this closed domain, I can still take the integral underneath this curve. But just because I can take the integral doesn't mean that the curve is continuous, all right? So this would be continuity implies integrability, but integrability does not mean continuity. And again, E and I and C are just standing for continuity and integrability. Okay, so if it's continuous, you can integrate it. Just because you can integrate something doesn't mean it's continuous. So just a few things to think about, but what we're going to do is this idea, apparently, this definite integral that we get from a Riemann sum, this definite integral is tied to area. What we're going to do is we're going to take a look at some shapes here, some graphs here, and we're going to see if we can actually integrate or determine what the area is. For instance, let's take this one right here. Oh, let's go from 1 to 4 of 1/2 x dx. Well, this right here, this is the function y equals 1/2 x. So what I'm really asking you to do, with a definite integral is I'm really asking you to find the area under the curve. So if I were to take a look at this function, I start at 0, 0. I go up 1 over 2, up 1 over 2. Turns out what I'm really asking you here is to find the area under this curve. Well, this curve, friends, it's just a triangle. So really all this is just figuring out the area of a triangle. The height of the triangle is 2, the base is 4. So it turns out what I'm really asking you here then is base times height divided by 2, which would be 4. So we can actually evaluate some of these definite integrals if we just realize a definite integral is nothing more than area. So let's have you guys try a few of these. We're going to try to go through and evaluate some areas. So how about let's do 0 to 5. That could be a fun one. That's x plus 2 dx. Let's try -4. See if you can figure out what shape these represent, and then use that to figure out the area. And how about 0 to 5 of x minus 3 dx. All right, friends, why don't you go ahead and pause the video here. See if you can figure out what area these shapes represent, and then determine the value of the definite integral. All right, let's see how you guys did. This one right here. I'm going out to 5. So 1, 2, 3, 4, 5. I have a y-intercept of 2. And if I go out to 5 and I plug 5 in there, 2, 3, 5, 6, 7. So all we're doing here is we're just taking this function right here, y equals x plus 2. I'm just graphing it. I'm going to find the area underneath this curve. And if I do that, I notice that this graph right here looks like a rectangle. So if I think of it in terms of a rectangle, I have a height, I have another height, and I have a base. So the area of a rectangle is the height times base 1, base 2, divided by 2. So I have 2. I lied, that's a 5. That's 2, and that's 7. So this is a trapezoid. 5 times 2 plus 7 divided by 2. So if I were to find the actual area of this thing, I believe it would be 45 halves. So that definite integral is going to be equal to 45 over 2. How about this next one? What shape would that be? Let's see here. If I were to think of it in terms of y equals, so y equals the square root of 16 minus x squared. Friends, that's the equation of a semicircle. So this shape right here, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, and 4. If I were to take the area of that, what all this shape looks like is the area of a semicircle. So the radius is 4. So pi r squared, and then divided by 2 because it's only half of 1. So pi r squared divided by 2. And we get 16. Oh, 16 pi over 2, or just 8. 8 pi. All right, let's try this last one here. What is that shape going to look like? All right, looks like I'm dealing with an absolute value function. So y equals the absolute value of x minus 3. So I'm going to graph that and see if I can't figure out what I'm actually looking at here. Two, 3, 4, 5. All right, so if I plug 0 in, I get absolute value of -3, which is 3. It's going to hit the x-axis at 0. If I plug 5 in, I get the absolute value of 2. So when I graph it, turns out I essentially get nothing more than just 2 different triangles. So this one is a 3, 3, so base times height divided by 2. This one, 2 times 2, so base times height divided by 2. So this area right here, 3 times 3 divided by 2, plus 2 times 2 divided by 2. It's just 2 right triangles. So 9, 4, that ends up being 13 halves. So we got some of these shapes that kind of pop up. It's kind of interesting. But we can evaluate these definite integrals because the graphs of their functions end up giving us some geometric shape that we know what to deal with. It turns out we got a couple of special properties that pop up. So we got some special definite integrals. Let's see. Our first one we have, and we'll see some examples of these here. How about we get, what if the upper and the lower bound were the same thing? The upper limit and the lower limit were the same thing. Turns out that value is always equal to 0. And if I ever want to switch the bounds, then it's going to take my area or my value of my definite integral, and it's going to just make it negative. So what are some examples of how this might work here? Say I give you a function. Oh, let's not use red. How about 3, 3? And I can give you anything really, or how about we go with -x squared plus 4? I don't even need to try to figure out what to do, because as soon as I see that these bounds are the same, I know that the whole overall area of this thing is 0. And the reason why I know that, friends, and again, I don't need to know what happens here, I mean, if I plug 3 in there, I'm going to end up with 3. So this right here, if I plug in my 3 to get my one of my values, negative x squared plus 4x. I plug 3 in for x. I get x equals 3, or y equals 3, sorry about that. But if you notice, if our upper bound and our lower bound are the exact same, what I'm really finding the area of is a line segment. A line segment, it's a rectangle that has no base. So the base is 0. So 0 times whatever the height would be 0. So that's why no matter, as long as the lower and upper bounds are the same, you don't have to do anything. It's automatically just going to be 0. I don't care what the function is. What about if I give you something like this? So let's think again what this graph looks like. We'll use that to help ourselves out here. 1, 2, 3, 4. 1, 2, 3, 4, 5. So from 0 to 0, we went up 2 and over 5. So that's 2.5. So that would be 2.5 is the height. And when I went this way, I went in a positive direction, so my base was 5. That's why we did base times height divided by 2. But notice, if I'm asked to go backwards, like this, it's kind of like that whole idea of velocity. When we go backwards, we go to the left, our velocity is negative. Well, in this case, then that essentially would take my base and make it a negative value. So then it'd be negative 5 times 2.5. Or what this theorem basically says is, so you don't get confused on positives and negatives, just put a negative out in front and you can switch the bounds. So now we have a negative out in front. We switch the bounds. Base 5 times height, which is 5/2 over 2, which is 2.5 divided by 2. We went backwards, so it ends up being a negative area. And some of you are like, wait a second, area can't be negative. You're right. So think of it more as displacement. A lot of times it's better to think of the word as displacement and not necessarily fully area. Okay, let's try a couple other little things that kind of come up here. We're just looking at some just random little principles that we can use with this these ideas of definite, integral, and area. The next one is called the additive interval property. So given 3 values, x equals a, x equals b, and x equals c, on a closed interval for f of x. So based upon that, here's what happens. If we have these things, and these things, if we have, well, should have been a C, not a 3, friends. Sorry about that. If we have 3 x values that we're dealing with on an interval, a closed interval, we have something that basically says, if I want to find the value from A to B, and all I have to do, friends, is sometimes it's easier to think of the value from A to C. And then from C to B. So let's go back and take a look at our absolute value problem we looked at. 1, 2, 3, 4, 5. 1, 2, 3. And if you remember, this was our graph for it. On this problem that we had before, we actually figured out the area from 0 to 5. And we treated it as two rectangles. No, two triangles. Well, sometimes it helps so we don't get confused. We can break it up as a first triangle. And as a second triangle. So if you wanted to keep the two parts opposite, you could have done that. You could have broken it up as two separate triangles because the result will give us what both triangles would be together. So we could have broken this up. So how's this potentially going to work for us? Say I give you something like this. Let's go from 1 to 4. Let's say that equals, and I don't know what the function looks like. I don't really care. Let's just call it 3. And what if I know that from 1 to 8, it equals 11? And I want you guys to determine the value from 4 to 8. All right, well, let's see how we can deal with this one. If you want to take a shot at it, go ahead and pause the video and see what ideas you can come up with, and then we'll look at it. So here's what I see. I see right here I have something going from 1 to 4. And then I see it going from 4 to 8. And if I were to add these two together, notice the lower of this one equals the upper of this one. So what I'm really looking at here is I'm taking it from 1 to 8. I can find that unknown region without even knowing it. So this purple one right here, that was equal to 3 plus, I'm looking for the value of the green one. And that's going to be equal to the value of the blue one, which was 11. No, it's just a simple linear equation, honestly. Written as integrals, definite integrals, sure, but it's just a little linear equation. That means this equals 8. Well, let's have you guys try one of these on your own here. Let me see if I can make it a little bit tougher on you. Oh, let's go from 2 to 5. And we'll let that be equal to 4. And let's go from 9 to 2. We'll let that be equal to 13. And I'd like you guys to figure this one out. Nine to 5. She's working 9 to 5. I tell you what. Oh, I forgot a DX on one of those, didn't I? All right. So now, first thing that should be going off in your head right now is bells and whistles. This one, it's written backwards. So we have to change it. So we're going to change that to 2 and 9. F of x dx. And when we change it, it becomes a negative value. So we'll let this one be our green one over here. And we'll let this one be our blue one right here. I'll get to the blue one here in a second. So if I take my 2 to 5, and I'm going to add 5 to 9 because I got to get up to my upper bound on my red one. Then that should get me to the entire way across. All right, so green, that was 4. Plus, got to find, I'm solving for the blue one. And it's going to be equal to the red one, which is negative 13. So when I move my green one over, I get 9 to 5. F of x dx equals negative 17. And again, we can have negative here just because the area is more displacement than area. And now if we look at it here, friends, especially my values here, notice my 5 and my 9 have flip-flopped. So now in order to make this match up, I'm going to have to flip-flop it. I invert my bounds. And by doing that, by inverting my bounds, it's going to take whatever my area was, and I have to multiply it by a negative number. That's where that negative kind of comes into play here. So negative 17 makes it a positive 17. All righty. Just a couple little more things here. We got a couple properties we can also kind of take a look at as well. There's all kinds of little properties, but let's just touch on a couple. We don't want to touch on too much. We'll touch on a couple here. All right, property. One of our properties says this. if I am multiplying a function by a constant, sometimes it's just easier to bring that constant out. And we'll see an example of this here in a second. And then our last thing we're going to look at here is sometimes when you're adding and subtracting two functions, sometimes it's just easier to break them apart into two separate definite integrals. A to B. Make sure that you give every person that dx, though. Plus or minus g of x dx. All right. So how's this going to work? Well, let's just toss on a couple problems here. So 3 times the square root of 4 minus x squared. And over here, let's do, what am I thinking here? I'm thinking from 0 to 6, 1/3 x plus the absolute value of x minus 4. All right, friends, go ahead and pause the video and see what you guys can do with this and see what you end up with. All right, so if I'm looking at this, the first thing I'm going to do is I'm going to go ahead and I'm going to pull my 3 out. So I pull it out of my definite integral. I just realized I forgot the dx on that, didn't I? And if this right here is going to be my y value, so y equals 4 minus x squared, square root of 4 minus x squared, I realize I'm dealing with a unit circle again. No, not a unit circle, but a circle. So the graph of that circle is going from here to here to here. It looks like that. So the radius is 2. So that means this would be 3 times pi r squared divided by 2, which is 6 pi. All right, on this one, it might just be a good idea to just break it up. So 0 over 6, or 0 to 6 of 1/3 x dx. Plus 0 over 6, or 0 to 6 of x minus 4 dx. And again, this is y equals 1/3 x. And this is y equals the absolute value of x minus 4. So let's graph these real quick. All right, 1, 2, 3, 4, 5, 6. 1, 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, and 4. So if we graph both these shapes, this one starts at 0, 0, goes up to 6, 2. And we end up with a base of 6 and a height of 2. And if I take this last one here, it'd have a y-intercept at 4, hits 4 here on the x-axis, and goes up to 2, 2. So it goes down, down. I have 4, 4, 2, 2. So 6 times 2. That'd be my triangle on the left, plus my series of 4 triangles here on the right. 4 over 4 times 2, plus 2 over 2 times 2. So 6 plus 8 plus 2 equals 16. All righty, friends. So when we take those Riemann sums, we find out they equal out to being a definite integral. And using what we know about geometric area, we can actually go and figure out the value of some of these definite integrals. So I'll see you in the morning. We'll talk more about it. And other than that, have a great afternoon.